All right, it's great to be here. My name is Andrew Howard. I'm at Caltech. I'm also the principal investigator for the Keck Planet Finder, and I'm here representing a big team. There's several members of the Keck Planet Finder team here in the audience. The beginning of my story is about a decade or more ago, and planet hunters like myself, we realized that we were starting to fall behind. And it's exemplified by the measurement of this particular planet. This is an artist's impression of Kepler 78b. We were really proud that this planet was discovered by the Keck telescope, and within a few months we had measured the mass of this planet, and we had showed that this planet had a density that makes it consistent with Earth-like composition. So this was the first instance in which we knew of a probably truly rocky planet outside of the solar system. Our measurements with Keck high-res are shown here on the right, and what you can see is we have a lot of measurements, and at the low and high quadratures, we're seeing an offset between those two that's indicative of the mass. There was a parallel measurement with the HARPS North spectrograph on a much smaller telescope, the 3.6 meter TNG. They also used half an hour exposures, had a similar number, and they measured more or less the same thing. So scientifically, this was really gratifying that we had a confirmation of our measurement. We had parallel papers in Nature. However, they had 1/8 of the collecting area. So how did they do this? The answer is that we have to really overexpose with Keck high-res to solve a 10,000 parameter model for each spectrum to reproduce the wavelength solution, the point spread function over the entire spectral format. The HARPS North spectrograph and other spectrographs simply hold the spectrograph still, so it doesn't require this elaborate model, and they can work at the photon limit. We decided to pursue a design that's a similar type. And so the things that we need to control to make the instrument stable are we need to basically have it hold absolutely still, control thermomechanical variations. We can't have the temperature of this, the instrument change and cause a mirror to shift slightly and the spectrum to shift, looking like a Doppler shift. Control pressure, we also have to control the optical illumination. We needed really high calibration. This led us to laser frequency combs, which I'll show in just a minute. And we also wanted to build an instrument that takes advantage of all of the aspects of the Keck community, including its really large aperture and its very broad community access. So I was digging through the archives and I found this old, now I guess about 8 years old, system overview diagram. I showed this to the Keck SSC in 2015. Here's our cross-dispersed shell design. The red camera was grayed out at that point. We had a slightly different vacuum chamber design. Fast forward a few years, we had advanced this design and started moving through our reviews, including the preliminary design review. The basic idea of the Keck Planet Finder is that we have a fiber injection unit which sits on the AO bench in the Keck 1 enclosure. And then optical fiber, literally a tube of glass, snakes down to the basement where the spectrometer lives in a location which is mechanically stable and relatively thermally stable inside a vacuum chamber. And this is where we make the high precision Doppler measurements. We have a set of supporting instruments. We have a calibration unit. We have a set of devices which homogenize the light as it's transported through the optical fiber. And we also have a sophisticated data reduction pipeline that will produce APJ quality results, which I'm going to show you in just a minute. So just to highlight 3 of the technologies that we use for the Keck Planet Finder. One is that we really took seriously the idea that we had to be immune to thermomechanical variations. So while the instrument is in a sarcophagus that keeps all the air out and keeps it relatively temperature stable, we also built it out of zero-dur glass, the same material from which the Keck primary mirror segments are made. So zero-dur, here's a little inset shot of one of the places where a vertical piece of zero-dur is mated to the zero-dur glass. All of the optics here are made out of zero-dur and they're coated on the other side. They sit on this optical table here. Zero-dur is about 1,000 times more thermally immune to temperature variations, that is how much it changes its length in response to a certain temperature change. It's 1,000 times better than the best metal out there, INVAR. So this was a great challenge. We also exploited optical fibers to transport the light and also to homogenize it to make sure that we illuminate the spectrometer exactly the same way every time, to a part in 10,000 in the near field and the far field. We exploited octagonal cross-section fibers, which are really good at this optical scrambling, so that no matter how you inject the light on the front end, you come out with a uniform illumination on the back end. Finally, we used a commercial laser frequency comb by Menlo Systems. The idea here is that you want to be able to tag every single pixel on your detector array with a very precise wavelength so that we can measure sharp Doppler shifts. This laser frequency comb, which is one of 3 Nobel Prize inventions in KPF, the others are CCD and fiber optics. The laser frequency comb produces a perfect picket fence in frequency space of emission lines that all have approximately the same intensity. This is way better than the case for, say, a thorium-argon lamp. So it was 8 years of development, and last summer we arrived with 2 shipping containers on the summit of Mauna Kea. Here we are sitting outside of Keck 2. FedEx has just dropped off the boxes. We had to reassemble strings, fibers all over the observatory, get the spectrometer inside the vacuum chamber, get the fiber injection unit on the Keck 1AO bench. And this culminated on November 9th of last year in our first light ceremony. This is inside the Keck 1 remote ops room in Waimea. It was a glorious night. Our first target was Jupiter. A lot of people have asked me what my experience was like on this first light night. And I'll say it was one mostly of relief. I was like, oh my God, thank God it works. I was just so happy and relieved that we not only got a spectrum, but that spectrum is high resolution and also high throughput. So during our commissioning, we started ticking off the boxes to demonstrate KPF's performance. One of the first things we did was measure the throughput of the instrument, and we found that it meets or exceeds our predictions. So as a function of wavelength, we reached throughputs that are nearly 10% or so for most wavelengths. We're missing a little bit in the blue, and we have some ideas about what this might be. Chuck had a good idea yesterday that we should check actually the reflectivity of the Keck primary and secondary and tertiary. The other main aspect of a spectrometer like this is you want to make sure that it's stable. So you can measure very precise Doppler shifts to detect these small planet motions. And so there's a few ways that we can do this. One of these measurements, we have to check the internal stability of the instrument, which is how much does the calibration fiber move in velocity space relative to the science fibers. So we can do these experiments where we illuminate with the laser frequency comb for a full day, make a huge number of measurements, and then determine velocity shifts of these laser frequency comb measurements, subtract the cal from our 3 science slices, and we see that we're at the tens of centimeter per second internal calibration level on a day-long scale. That's extremely encouraging, but we wanted to see what it looks like on actual starlight. So I'm going to demonstrate this in a couple of ways. The first way is using one of the subsystems of KPF, which is called the solar calibrator. Ryan Rubenzahl is going to give the first talk immediately after lunch, and I encourage you to come to that to hear all about it. Let me just steal just a little bit of his thunder and show that in this 2-hour observation of the sun, so pointing a lens at the sun and collecting that light in KPF, first of all, in gray, you see that there are these solar oscillations. That's the 5-minute oscillation period of the sun. But if you average that out, as we do with stars, the performance of KPF on a real star, i.e. our sun, is 26 centimeters per second over this 2-hour period. So we're really impressed by that. The second example I'm going to give is of a standard star, which is called Sigma Draconis. These are observations for which Dan Huber is the PI. Sigma Draconis is a well-known bright K-dwarf in the north. And we looked at SIGDRAW for about 7 hours straight using a special fast read mode on KPF. And the first thing you notice is that the RMS of this is 40 centimeters per second. So that shows that as an instrument, KPF is performing well. But what's amazing is that a lot of that 40 centimeters per second is signal. If you take the essentially the Fourier transform of this, compute the power spectral density function, you see that most of the power, that is, most of the frequencies at which these velocities are wiggling, are basically exactly where we'd predict. There's a forest of peaks here at about 4,500 microhertz. These are the equivalent of the 5-minute oscillations in the sun, but they're oscillations in this K-dwarf. And using the pattern of these modes, you can determine fundamental internal properties of Cygnus Draconis. This is something Dan is working on. But what's impressive to me, especially just from an instrument builder perspective, is that we're measuring the highest peak here corresponds to a 14 centimeter per second signal for that mode. The modes in the noise part of the spectrum are more like 2 centimeters per second. You have to add up all the different modes in the noise, so that's not exactly a statement of what our noise is. Nevertheless, we're impressed. Let me show you a couple of results from transiting exoplanets. KPF is performing extremely well on short time scales of a night. I'll tell you at the very last slide about our performance on longer time scales. So here's a couple examples of, this is a young planetary system with 2 transiting planets. It's called TOI 4495. It was discovered by TESS. The youth in this system makes it interesting because this allows us to tell something about the orientation of the planet's orbit relative to the stellar spin axis. We very easily see the Doppler shifts of a Rossiter McLaughlin effect as the planet passes over a blue shifted and then red shifted part of the star. We see it in this sort of classical representation of the data. We also see it in what's called reloaded RM, where you look for a little dip to float through the average line profile. And so that's what we're seeing here by this shadow crossing line profile as a function of time. We started to take advantage of the huge aperture of the Keck telescope. One of the challenges with these transit measurements is that you only have a short amount of time. You can't just integrate forever. It's especially hard for M dwarfs where the stellar diameter is relatively small, so the planet passes quickly. This transit only lasts an hour. This is actually the first hot Jupiter around an M dwarf, and this is work by Gumi Stephenson. The star is also extremely faint by planet hunting standards. It's about 16th magnitude in V. Nevertheless, especially using KPF's reddest wavelengths, we clearly see this transit. We're able to show that it's a prograde aligned orbit, and that's a scientifically compelling story. So we're starting to measure masses of planets with KPF as well. Here's one example from Fei Dai and his NASA KSMS program. This is an ultra short period planet. The orbital period is about a quarter of a day. And compellingly, just like Kepler 78b, this is a 1 Earth radius planet. So we see that the radial velocities are starting to phase up here. This target is scientifically compelling because it's one of the best planets that JWST can get surface reflection of to try to determine the mineralogy of this planet. Is it made of post-perovskite, or is it made of granite? Is it made of something else? We can now start to do rudimentary geology with JWST, but in order to do that, we need the mass of the planet, and that's where KPF comes in. So I'll close here on my last slide and highlight an area that we need to work on, which is that while we have extraordinary short-term stability, we're still working to string together many nights in a row and understand the offsets between the nights. So here's an example of that same star, Cygnus Draconis. We have about 1.5 meters per second RMS over a couple months. Let me give a huge mahalo to everyone on the KPF team, the WMKO staff, astronomers, everyone at the observatory. It's really been fantastic to work so closely with everyone, especially in this last year as we brought the instrument to fruition. So I will stop there and take questions.